Hi there, Algebra 2A Padawans. This is Mrs. Bird. I am going to be walking you through today um, Project 5, essentially the first part of Project 5 that you see in Lesson 21 here. All right, what I have done is I have copy and pasted each question into just a Word document because it's a little bit easier for me to go ahead and then I just have this clean white space that I can use to show you my work versus trying to do it in courseware where it's just a little bit congested. So you should see the exact same questions and it should all it should be exactly the same. All right, we're going to just jump right in. And it starts out with giving us just a little bit of background information, saying Gottfried and Bernard are dragons. Oh, good for them. Their friend Henrik, a meerkat, is having a party this evening, 317 kilometers away. Luckily, they're dragons. 317 kilometers, that's a long ways away. But they're dragons, they're going to fly. It won't take them very long. Good for them. Yippity doo. Wouldn't that be cool to be able to fly? I guess I'm just jealous. All right. So it says when Gottfried flies, he refers to take off at a 9-degree angle, maintain a cruising altitude of 12 kilometers, and then come in for a landing at 5 degrees. So luckily, they have actually drawn this for us down here. So here is Gottfried. He flies off at an angle from the ground. That's what A is the ground. Takes off at an angle of 9 degrees until he gets high enough above things where he won't run into them, which he's saying is 12 kilometers. So this would be the height off of the ground, 12 kilometers. Maintains that until he's ready. He's got Henrik's the meerkat's house in his eyesight, and then he starts to descend, but at a smaller angle, which is 5 degrees, until he lands at the old meerkat party. And then it gives us a little bit of information about Bernard. On the other hand, he likes to take off at a steeper angle, stays a little bit higher, and then come in at an angle of 4 degrees. So we're going to probably be comparing Gottfried's flying versus Bernard's flying. So in question 1, we're going to use this diagram for Gottfried's flying path. Knowing, I'm going to just scroll down a wee bit, that the horizontal distance corresponds to the part where the trip where Gottfried's altitude is increasing to A, the horizontal distance that corresponds to the part of the trip where he's screening. Okay, yeah, so what this is saying is that A is corresponding to where he's just increasing, he's gaining in altitude. B, down here, corresponds to when he's just hanging out, flying straight high in the sky. And then C corresponds to where he's starting to decrease in altitude or come down for a landing. So that's all that wording is saying there. So we're going to use this information to approximate the value for A. Now, the beautiful thing about their drawing and the way that they've described it is that I see these amazing right triangles. So if I looked at this triangle right here, I should see obviously 90 degrees. 90 degrees, ding, 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 big bell ringer for me. I can use SOHCAHTOA. Ooh, that's large. Large and in charge. I don't need that big. I can use SOHCAHTOA anytime that there is a 90-degree triangle. So SOHCAHTOA. It's not like a fancy name. It's a way of remembering our trig functions of S is for sine. So sine is a trig function. Oop, I thought that would happen. And then we have these relationships for each trig function. So sine has a specific relationship with a triangle. Cosine has a different specific relationship, and so does tangent. The O part of so helps me remember what that relationship is for sine. So this could be a nice little review. Sine of some angle, I'll call this angle theta, that's a Greek letter. The O part is coming from whatever the opposite leg is of that triangle over the hypotenuse. So that's the OH part. And then we got CA for cosine. We got cosine of some angle. The CA part is the adjacent leg over the hypotenuse. And then good old tangent of some angle. The OA part is the opposite leg over adjacent. So it's just a nice little acronym or funny word saying, I guess, to help us remember all of those relationships. So as I look at solving for A, I'm noticing that A is a leg in that first triangle, but it's the leg adjacent or right next to that given angle of A. And then I don't know the hypotenuse. Remember, hypotenuse is always opposite of the 90 degree. It's the long guy in that one. But I do know the side that is opposite. So I do know, I'm trying to find adjacent. I do know the opposite. So that would actually lead us to the tangent relationship. So that's what we're going to use. Tangent of 9 degrees is equal to opposite, which is 12, over adjacent, which is A. That's what I'm trying to solve for. All right, now we just solve for A. Being in the denominator, I'm going to just multiply by A to kind of creep it out of the denominator. That's my strategy. Because at least now I don't have any fractions to deal with. And now I can clearly see that tangent is multiplying, so I'm going to just divide. Two-step process there, but it just makes sense for me, so that's the way that I've always done it. So A is equal to 12 divided by tangent of 9 degrees. Now, you do not need to memorize any of these SOHCAHTOA relationships. We're going to just use a calculator here. So I have here the Desmos. This is just straight up desmos.com. So what you want to do is I would just use this scientific calculator. We're not trying to graph anything. We're not trying to be fancy. Just go to your scientific calculator here. And I know all of my stuff is still here. But what I'm trying to find, if you remember, is the tangent is 12. Let me write it up here. As soon as I do that. What we're trying to find is 12 divided by the tangent of 9 degrees, if you remember that. So I just typed that right into here. Heads up, there is a couple of different ways of measuring angles. We're measuring it right now in degrees. So you want to make sure that this guy says degrees right here. When you swap it, see how it says rad? We're not in the rad world yet. So make sure that it's saying degrees. And then now I'm just going to type it in like I would anything. 12, I'm going to divide that. See how it gives me a fraction? Oh, sweet. Thanks, Desmos. Tangent. Oh, see how it gives me a parentheses? Man, I love Desmos. 9. And then remember, it's already in degrees. Perfect. Answer 75.76. Boom, boom, pow. So all of that to say, A, that's what we were solving for. A is equal to 75.76. All right, there is your question 1. Beautiful. So I'm going to scroll down and I have copy pasted question number 2. So we're referring to the previous question using all of that same information. Now in the project, it does not bring down this image for you, but I'm a visual person. I like to have that. So maybe even sketch that out on a piece of paper for yourself, or you can always just flip back into the question and kind of glance at it. But I just copied it here because it's going to be a pretty sweet deal for me. And here we are trying to find, excuse me, the value of C. All right, so we're solving for the green guy. Green guy. All right, so I'm going to use the same strategy that I did with the first one. I have an angle in a right triangle, so I'm probably going to use some sort of SOHCAHTOA relationship. I'm trying to find the side that is adjacent, and I know nothing about the hypotenuse absolutely nothing. But the adjacent leg, wow, not adjacent, the opposite leg, it's not giving me information either, except I am starting to recognize that this is 12. Sorry, my dog just opened the door. 12, this is a big old rectangle, right? He's flying at a specific horizontal altitude, so these have to be parallel. So this guy over here needs to be 12 kilometers as well. Ah, pretty sweet, huh? Nice little geometry. We got a beautiful rectangle right there. So then that brings me to back to this guy. And I know the adjacent side. I'm trying to find the adjacent side. I'm sorry. I don't know that. But I do know the opposite side. So that's tangent again. So tangent of 5 degrees is equal to, what would that be? Opposite, 12 over c, which is what we're trying to solve for. So my strategy again, multiply both sides by c. That way it gets rid of the fraction. Then I can see very clearly that I'm multiplying c by tangent of 5 degrees. So I'm going to just divide it. So c is equal to 12 divided by the tangent of 5 degrees. Wham! I got something to type into my calculator, so I'm going to jump to Desmos. And I'm going to type that in. I was just here, remember that? So I still have that 9 in there. I'm just going to delete that and then type in a 5. There it is, 137.16. I believe that we were asked to round it. So C is equal to 137, no. What was it, 0.16? I think it was, right? 16, round it to 2.2. How's that? 0.2, right on. All right. All right, question number 3. All right, question number 3 now. Moving down. So I have done the same thing in question number 3. I brought down my little image because, again, visually, I like to know what's going on. So refer back, switch back to question number 1 to get that diagram, or just sketch one out on a piece of paper. Okay. So number 3, it's given us a little bit of like, hey, remember that the horizontal distance between Gottfried and Henrik's house, remember the meerkat? So we got Gottfried's home, we got, what was his name? Henrik. His house over here. Total distance between them is 317. 317. So that looks like if I added the lengths of A, B, and C, which comprises of that entire side, it has to be 317. So we are asked to find the value of B, but we need the previous 2 questions. In question 1, we actually solved for A. So if you didn't catch that piece and you're just joining this video, go ahead and back it up. But we solved for A already, 75.7. I think I had a 6 actually. There we go. And then we solved for B to be 137.2. So I'm going to just use my substitution rule. I know what A is. It's 75.76, so I'm going to plug that in. No idea what B is yet, but C, substitution. Oh, wait. I messed up. This is a C. There we go. We solved for A and C previously, but not B. All right, so with C, I can use substitution and plug that in. Cool. So now it's just 2-step equation to solve. I notice that I have 2 numbers. Numbers are like numbers, so I'm going to go ahead and combine those like terms. And when I do, I get 212.96 plus b is equal to 317. Okay, so that's adding. So the inverse of addition would be to subtract, or that's going to cancel this guy out. What I do to one side, I do to the other. So that leaves me with just b on the left-hand side, and grab a calculator, jump over to Desmos to get this guy, but we get 104.04, but I believe that the solution that it wants is, it just rounds it to 104. All right, so there is answer for number 3. I'm going to move on to question number 4. All right, here we are at question number 4. Get myself a little bit more working room. All right. So question number 4, Gottfried is when he's at his cruising altitude. So remember when he takes off, he's taking off. Why does it want to move? And then he's at that cruising altitude right here. That's where he's like not going up and down. He's maintaining the same height or altitude above the ground. So when he's hanging out right here above that segment of B, it says that he's going a speed of 225 kilometers. So I'm going to use S for speed of 225 kilometers. All right. Approximately how much time? So that's what we're solving for. Time. Well, I don't know. I don't know what that is. Does he spend at the cruising altitude? So it says, remember, speed is equal to the distance divided by time. Now that is actually coming from an equation that I memorized back in my day as the DIRT equation. Distance is equal to rate times time. Now I used S for speed. Rate and speed are the same thing. I think old school teachers just liked the DIRT kind of way of helping you memorize it. So here they're saying that the speed, or remember in my equation, rate, here I'll use that guy. They're saying speed is equal to the distance traveled divided by time. Well, I could have used that same DIRT equation to just manipulate it to solve for the speed just by dividing. So same thing. All right, we're going to use that equation, speed or rate or whatever you want to think of it as distance being divided by time. It does say pay close attention to the units because all of the answers given to you as possible solutions, all of the units that they use is in minutes. And that becomes a problem here because the speed that they gave us is 225 kilometers per hour. It helps when I finish this. Speed is 225 kilometers per hour. So we have a conflict of units. We got hours and we have minutes. So I am going to convert 225 kilometers per hour to be 225 kilometers per minute. So to do that, I like to set up a ratio table. 1 hour. 225 kilometers per 1 hour. Now, what do I need to multiply? Well, I know that 1 hour is equal to 60 minutes. Now, I knew that I needed to put the hours in the numerator because hours in the denominator with the numerator will they'll cancel. So now when I multiply my fractions straight across, I get 225 kilometers per 60 minutes. So now I got my unit that I want, but I just want to simplify that. So I've already divided that. 225 divided by 60 is 3.75 kilometers per minute. Okay, so now we have a speed of 3.75 kilometers per minute. And now we have the right units to just use our little formula here. Speed is 3.75 kilometers per hour, and that's equal to the distance of B. Remember, he's flying up above B at that same altitude. If you remember, we just solved for B in the previous question, and we had 104, right? I had 0.04, but they rounded it to 104. So we'll stick with that. And we are solving for the time. Okay. Great. Now I just need to solve for t. So what I'm noticing here is that t is in the denominator. I just like to cancel. I'm just going to get rid of the fraction. To multiply both sides by t, that cancels out the fraction piece, which to my brain is a little, I don't know, it's just not very friendly to my brain. So as soon as I do that, now I can see very clearly that if I just divide again by 3.75, I get my t all by itself. So t is equal to 104, divide that by 3.75, and when we do, we get 27.7, and our final units for time is minutes. Great. Okay, reach out to me if you have any questions there for question number 4. And question number 5, let's take a look at it. Okay, so in question number 5 here, it says, explain how you can modify those strategies for finding the amount of the time Gottfried was cruising altitude. So it's essentially saying, use what you just did with Gottfried to figure out what Bernard is doing in his flight pattern. So I'm not going to do this all for you, but I will get you started here. My number 1 hint is to draw a picture. So we're asked to remember, thank goodness, because I did not, his takeoff angle is 11 degrees. So remember, we got some distance from Bernard's house to Henrik's house that he's needing to go. And his takeoff is 11 degrees. Now, I'm not a beautiful artist, but there's my 11 degrees. And then he reaches a cruising altitude of 13. So that means that high above the ground, measured at 13 at a 90-degree angle, is 13 kilometers. Then he cruises along for some amount of time, which we don't know. But then right here, again, 90-degree angle, he starts coming down to 4-degree at a 4-degree angle. All right. So what I would suggest you do is, just like the other diagram, label each of these segments, A, B, and C, knowing that they are 317 miles apart. Nope, kilometers. We're an imperial. So A plus B is 317. So what you want to do is just use those strategies that I've shown you in questions 1, 2, 3, and 4, and explain how you might tweak or alter those strategies with Bernard's information. All right. Hopefully that really helps you through this first part of the project. Reach out to me if you have any questions, and as always, have a great day.